So I'm Francisco Chicano from the University of Malaga. Good morning to everyone. This is a work done with my colleagues in Houssem, Eddine, Smida, which is my PhD student, and Saoussen Krichen from the University of Tunis. And it's called Iterated Granular Neighborhood Algorithm for the Taxi Sharing Problem. It is a work that was mainly done by our student, but he couldn't attend the conference and I'm doing the presentation. So I will use the pointer here. So due to the global warming of the Earth, there is an increasing interest in saving resources and reducing the pollution nowadays. So this is one of the goals of the smart mobility dimension in the smart cities field. And one of the ideas that have been proposed is to share some trips to use less pollution and also reduce the consumption and economic savings. One of the problems that have been proposed is called taxi sharing, and the idea is to share taxis from going from one point to different destination. This problem has been solved using evolutionary algorithms in the past, but also exact algorithms. And the idea is as follows: imagine that we have a set of people in an origin, and they want to go to different destination or the same destination. It depends on the preferences, and they want to share taxis. But the taxis have a maximum capacity of people, and they also have a minimum fare they have to pay in addition to the travel distance cost. This problem, this is the fitness function, is just the sum for all the taxis of the minimum fare plus the cost of going from one place to another. And it is not difficult to imagine that this is NP-hard because it's related to the vehicle routing problem and the travel salesperson problem. So in this work, we propose an iterated local search algorithm. First, the representation of solution that we use is an array of integers where the zero values are used as markers to differentiate the different taxis. And the other number, the non-zero values, are the passengers going to their destinations and the order in which they are taken to their destinations. The iterated local search is using a special neighborhood that is called granular neighborhood, and that's why we also call this algorithm iterated granular neighborhood. And it works as follows. First, we generate a random initial solution. We will talk about this in the next slide. And then it applies a local search, exploring the neighborhood and try to improve the current solution. It's a first hit local search. And then it enters a loop in which it tries to, once it finds a local optimum, it tries to perturb the solution to go out of the local optimum, to escape from the local optimum, and applies again local search. The new local optimum is accepted only if it is better than the previous one. And this is iterated until the stopping condition is reached, which now experimented usually this runtime. For the initial solution, what we do is we generate a random permutation of the passengers, and then they are introducing in taxis in order. But we introduce passengers until we exceed the capacity of the taxis, or if we find that it is better to start from an origin to a destination rather than following the same taxi, we also start a new taxi. For example, in this solution, we take the first passenger 3 in the first taxi, and then to add 7, the passenger 7, we analyze if it is better to start from the origin to 7 to the destination of 7, or we should go from the destination of 3 to the destination of 7. Whatever is lower in cost is what is done. In the second case, we just, in the case in which we need a new taxi, we generate a new taxi for this. So then we use a local search with a granular neighborhood. This was a neighborhood that was proposed by Toth and Vigo for the vehicle routing problem. And the idea is to only use those arcs that have a length lower than a given threshold, which we represent with bar theta in our formulation. So there are 2 constraints that we have to fulfill in order to consider the swaps, because this is a kind of swap neighborhood with some constraints. The first is that we cannot exceed the capacity of the taxis. So for example, this swap is not allowed because it generates a taxi with 5 passengers, and this is not allowed. The maximum capacity is 4. And the second constraint is that we only allow swaps in which we use the arcs that have a cost lower than the given granularity. So if the cost is exceeding the granularity by theta, then this swap is not allowed. Then in order to go to the next solution, we need to have a better solution. So we only move to a new solution if it is better than the current one. So it's a first hit local search. So this is the idea of the granular neighborhood. We just avoid those arcs that are very large. And to determine this parameter bar theta, we just compute the cost of the initial solution, divide this cost by the number of passengers and plus taxis, and multiply by another parameter, which is beta, that in our experiment is 5. So just to show some experiments, we use 24 real-lag instances used by Masovio et al. In the paper of 2014, so using evolutionary algorithms. These are generated with a taxi query generator based on trajectory for more than 10,000 taxis in Beijing, China, with the sizes from 9 to 70 passengers. And we use the Iterated Granular Neighborhood Algorithm, which is the proposal here. We also solve small instances using CPLEX with a mixed integral linear programming formulation. We compare with a parallel microevolutionary algorithm that was used in the previous work with the best configuration of this algorithm. And as stopping criteria, we mainly use runtime, except for the small instances where we try to find the best optimal solution. And this is the machine used in the experiments. So for small instances, up to 25 passengers, we find that this is very easy a problem. And in fact, CPLEX can solve it exactly in a few seconds, except for the larger instances. 25 instances is too much. So we cannot find an optimal solution in these cases. But the evolutionary algorithm and our algorithm also find this global optimal solution in a very short time. So these instances are small and it's difficult. Well, both algorithms, or the 3 algorithms, are good in all of them. When we go to medium instances, in this case, we stop by runtime and we use the runtime of the evolutionary algorithm because we couldn't run the evolutionary algorithm again. We just are using the result of the literature. We stop our iterative granular neighborhood algorithm using the same runtime. And we find that the average values of the cost is lower than in the case of the evolutionary algorithm. So we notice a slight improvement using our algorithm. The same happens for large instances and for very large instances. We also see that the average in all the cases is improving the average obtained by the evolutionary algorithm. We did some statistical tests to check if these observed differences are statistically significant or not. And we found that for small instances, the differences are not significant because they all get the optimal solution. But in the case of a medium, large, and very large, we find that all the p-values are below 0.05. So they are statistically different, except in the large instance number 4. So as conclusion, we have seen that the CPLEX and the 3 algorithms are good for this problem in small instances, but for medium, large, and very large, the iterative granular neighborhood algorithm proposed here outperform the evolutionary algorithm, and the CPLEX is not able to solve these large instances. In the future, we will plan to extend the formulation to include more realistic scenarios like real-time traffic, passenger train constraint, multiple origins. And we also I'm trying to provide a parallel implementation of the algorithm. And that's all. These are the sponsors. We also thank to the authors of the previous paper. And if you have any question, as this is a very short talk, 10 minutes, you can find me in the poster session tonight and tomorrow night at this URL. Thank you very much.